Welcome, architects. Today, we view cosmology through the lens of ultra-scalable infrastructure. Our current model, Lambda CDM, represents the ultimate legacy system, initialized 13.8 billion years ago. In this session, we will treat the Big Bang as a massive cold boot event, where the universe transitioned from a singularity to a distributed state. We are seeing logs from the James Webb Space Telescope that suggest our initial configuration files might be corrupted. As engineers who manage high availability, you understand that even a minor misconfiguration at startup can lead to catastrophic failures at scale. We are now at a crossroads where the documentation of physics no longer matches the production environment of the deep cosmos. Let's debug the universe. In distributed systems, achieving global consensus across distant nodes is a major challenge. The horizon problem represents a massive data consistency error in the early universe. When we look at the cosmic microwave background radiation, it is remarkably uniform at 2.7 Kelvin across the entire sky. From a networking perspective, this is impossible. These distant regions were never in network contact to sync their thermal states, yet they are identical. This suggests an inflationary period, a massive horizontal scaling event that pushed nodes apart faster than the speed of light, which acts as the universal latency floor. If we cannot explain this sync, our understanding of the universe's load balancer is fundamentally flawed. Every robust architecture has hidden dependencies. In the cosmos, 27% of the mass energy density is attributed to dark matter. Think of this as undocumented middleware that provides the gravitational glue to keep galaxies from flying apart during high-velocity rotations. It doesn't interact with the electromagnetic spectrum. No logging, no headers, no trace in the UI. We only know it exists because of the load it puts on the visible system. Without this shadow infrastructure, the galactic clusters we observe would lack the structural integrity to maintain high availability. We are currently trying to reverse engineer this middleware to understand why it accounts for such a massive portion of the system's total overhead. The James Webb Space Telescope recently discovered massive galaxies at redshifts of Z greater than 10. For infrastructure engineers, this is like finding fully populated, high-traffic databases only milliseconds after a system wipe. According to our legacy models, these structures shouldn't have had enough time to form. This suggests a cache invalidation error in our theories of star formation. These impossible galaxies are too large and too mature for their timestamp. We are seeing legacy data in what should be a greenfield environment. This discovery forces us to rethink the right latency of gravity and how quickly matter can cluster into complex systems in the early stages of the universe. One of the most significant P0 bugs in astronomy today is the Hubble tension. When we measure the expansion rate of the universe, the Hubble constant, using different monitoring tools, we get conflicting results. The early universe telemetry, CMB, gives us 67.4 kilometers per second per megaparsec, while late universe telemetry, supernovae, gives us roughly 73.0 kilometers per second per megaparsec. In system design, this is a classic split-brain scenario. Your monitoring tools are disagreeing on the primary system metric. This 9% discrepancy is not just a rounding error, it's a statistical significance of over 5 sigma. It suggests that our expansion API might be changing versions, or that there is a physics-level bug we haven't patched yet. If dark matter is the glue, dark energy is the expansion pressure. It accounts for a staggering 68% of the universe's total energy density. From an infrastructure perspective, this is a runaway scaling process. Instead of the system reaching a steady state, the space between nodes is expanding at an accelerating rate. This is like a cloud provider charging you for more storage, space, even when you aren't adding data. This expansion is so aggressive that it will eventually lead to heat death, a state of total resource exhaustion where no work can be performed. We are trying to determine if this is a constant lambda value or a dynamic scaling factor that could change over time.
Given the fine-tuning of universal constants, some architects propose the simulation hypothesis. Is the universe a containerized instance running on a higher-order substrate? We see quantization at the Planck scale, essentially the bit depth or resolution of the simulation. When we look at black holes, we see data being compressed onto a 2D event horizon, much like a holographic disk. This suggests the universe might have a maximum I/O throughput and memory limit. If the universe is a simulation, the anomalies we see, like the Hubble tension, might be patch notes or edge cases that the system's root admin is currently debugging. We are looking for the source code in the laws of physics.
To resolve these critical system errors, we need a unified theory, the ultimate software patch that merges general relativity with quantum mechanics. Our current documentation works for macro-scale infrastructure and micro-scale services, but they are incompatible at the kernel level. As we gather more telemetry from next-gen observatories, we must be prepared for a major version release of physics. This might involve introducing new dimensions, additional nodes, or modifying the gravitational API. The goal remains the same: a stable, high-availability model of the cosmos that accounts for all 13.8 billion years of system uptime. The universe isn't broken. Our README just needs an update.